Welcome back, Russ Jackson. We're diving deeper into Rust's approach to concurrency today. What's the core idea behind fearless concurrency?
Well, Matthew, the core is this. Rust aims to make concurrent programming reliable. It wants to prevent those nasty bugs that often crop up in concurrent code.
So, you're saying it's about compile time error detection instead of runtime issues?
Exactly. Rust uses its ownership and type system to catch concurrency problems at compile time. Imagine a bank transfer. If your code has a hidden error in how it handles those concurrent transactions, Rust's compiler will shout at you, saving you headaches later.
That's impressive. Can you give me a practical example? Like, say, a trading platform?
Sure. In a trading platform, multiple threads might be simultaneously processing orders. In a poorly designed system, you could end up with data races, where different threads try to access the same shared resource at the same time, potentially corrupting data. Rust's compiler would flag these issues, preventing crashes during critical periods.
Makes sense. What about different approaches for handling concurrency, like message passing versus shared state?
Rust supports both. Message passing, where threads communicate by sending messages, is great for decoupling tasks. Shared state, well, that's when threads directly access and modify the same data. Rust lets you pick whichever approach best fits your problem. It's like having a toolbox with different kinds of tools.
So, Rust provides flexibility. But are there trade-offs?
Absolutely. Message passing can be more complex to implement than shared state approaches. But it often leads to cleaner, more predictable code, which is crucial for preventing errors in a high-stakes scenario like a financial platform.
How does Rust help with user-defined types and concurrency?
The sync and send traits are key. Sync guarantees that a type is safe for concurrent access, while send ensures that a type can be sent between threads without causing issues. These traits help users know when they are safe. This is so helpful for writing robust and safe applications.
You mentioned that other languages are dogmatic in their approach to concurrency. Why is Rust different?
Other languages often favor one specific approach, message passing or shared state, and make it hard to do others. Rust empowers programmers to choose the correct method based on the problem. It gives you more freedom, which often leads to higher performance solutions.
It sounds more versatile. What are some pitfalls to watch out for when using Rust concurrency features?
One issue is understanding the different concurrency models, both message passing and shared state, and correctly applying the tools. Another pitfall is overlooking the need for sync and send traits, which can lead to unexpected errors.
Thanks for clarifying those points. It's quite a deep subject.
It is, but the benefits of fearless concurrency in Rust are pretty appealing to programmers working on financial applications where even small mistakes can lead to big problems.
So, the core concept is not just about speed, but about safety and preventing future issues?
Exactly. Rust's concurrency features aren't just about handling multiple tasks, but doing it safely, robustly, and predictably.
Fantastic insight, Russ Jackson. Thanks for shedding light on this critical aspect of Rust.
Thanks for having me, Matthew.
Hey, Russ Jackson, welcome back. Let's talk threads. You were mentioning how important they are in a program, but also how tricky they can be.
Yeah, threads are powerful, but managing them can lead to headaches. Think of them as mini programs running simultaneously inside your main program.
So, like little worker bees?
Exactly. Each thread has its own little task to complete.
But why not just have one big program?
Well, for complex tasks, splitting the work into threads can speed things up dramatically. Imagine processing a massive dataset. Using multiple threads to analyze different parts of the data at the same time could take significantly less time compared to doing it all in one thread.
That makes sense. But what's the risk?
The simultaneous nature of threads is what creates the problem. Imagine several threads trying to access the same data at the same time. That's a recipe for a disaster.
Like a data race? Can you elaborate?
Yeah, a race condition. If the threads aren't coordinated properly, they could end up overwriting or corrupting shared data, which could lead to unpredictable results. Imagine trying to update a bank account balance simultaneously from different threads.
Whoa, that's a real problem.
Absolutely. And then there are deadlocks. A thread might be waiting for a resource held by another thread, and vice versa. They are both stuck, and nothing progresses.
So, Rust has ways to avoid this?
Rust does have tools to help manage threads and minimize problems. It promotes a specific kind of thread management, often called 1:1, where every thread in the program directly maps to a dedicated thread of the operating system.
So, fewer headaches.
Exactly. This is different from some other systems which can have many threads in a program, but they might be mapped to fewer operating system threads. But Rust doesn't do that to avoid complex runtime systems.
How does Rust handle the situation if you really need that other threading model?
There are crates, external libraries, available that provide more flexible thread management, where you can have multiple program threads mapped to fewer OS threads to gain efficiency.
So, flexibility is the trade-off with more complexity in the program?
Correct. It's a trade-off between simplicity and potential gains in performance. In many situations, the simple 1:1 model is sufficient.
This seems like a key concept in making programs robust, especially when considering financial applications.
Definitely. Managing concurrent access to data and resources is critical for financial systems. Threads might be involved in verifying transactions, updating balances, or checking for fraud.
So, Rust helps with that, right?
Exactly. This allows for safe and reliable financial applications.
Great explanation, Russ Jackson. This is really helpful in understanding thread management and its potential impact on programming design.
Thanks, Matthew.
Russ Jackson, welcome back to the show. Today we're diving into threads in Rust. Pretty cool, huh?
Absolutely. Threads are fundamental to modern programming, especially when dealing with tasks that can run independently.
So, tell us about creating a new thread in Rust.
We use thread, spawn. It takes a closure, a block of code, and runs it in a separate thread.
A closure? Can you elaborate?
A closure is like a mini function, but it can capture variables from its surrounding environment. Think of it as a function with a memory of its context.
So, what's the code do in the example?
The main thread prints some numbers, while a new thread created with spawn prints a different set of numbers. Thread, sleep pauses each thread briefly, allowing the OS to switch between them.
So, the threads might not run in perfect order?
Exactly. The operating system schedules threads. The order in which they execute depends on factors like CPU load and the OS scheduling algorithm.
Is that a problem?
Not necessarily. It's how we can handle tasks that might run longer, making your program responsive.
Can you connect this to a financial application?
Imagine processing a batch of transactions. We could spawn a new thread for each transaction. This way the main thread doesn't wait for one slow transaction.
What about if one thread fails?
That's a critical concern. The failed thread will affect the whole application if we don't handle it properly. We should gracefully handle the failure to prevent issues.
What if the main thread exits before the new thread is done?
The new thread will be stopped when the main thread ends, in this example. It's a limitation to keep things simple. More advanced programs will likely manage threads differently.
Got it. So, increasing the loops could help us see better multitasking?
Exactly. The sleep functions create more opportunities for the operating system to switch between threads, resulting in better overlap and a more demonstrably concurrent execution.
What are some common mistakes people make with spawning threads?
A common mistake is not considering the thread's lifespan in relation to the main thread. There's a lot more nuance to robust multi-threading, like synchronization and shared memory management.
Great insights. Let's talk about those nuances in a future episode.
Sounds good.
Thanks, Russ Jackson, for that explanation. Russ Jackson, welcome back to the show. Today, we're diving deeper into thread management in Rust. You mentioned join handles earlier. Can you give us a quick refresher on what they are?
Sure, Matthew. A join handle is basically a handle to a spawned thread. Think of it as a ticket that lets you track the progress of a thread you launched.
So, it's like a way to monitor the thread?
Exactly. Crucially, it allows the main thread to wait for the spawn thread to finish its work before continuing. Without it, the main thread might exit prematurely, leaving the spawn thread hanging.
Okay, and how does join come into play?
The join method on a join handle blocks the current thread until the thread it refers to has completed. This is super important for making sure your program doesn't crash from an incomplete task.
So if you put handle.join.unwrap after the thread creation, the main thread pauses, right?
Precisely. It waits for the spawn thread to do all its work.
What if you put that line before the for loop in the main thread?
Then the main thread waits for the spawn thread to finish, and only then does it proceed with the loop. The order of execution fundamentally changes.
That's a major point. So, the placement of join directly impacts the interleaving of thread outputs?
Absolutely. The output sequence changes dramatically. Imagine trying to manage a complex financial transaction. If you prematurely close the main loop, you lose vital information in one thread.
Right? The financial analogy really hits home. What's a common mistake people make with threads and join handles?
Not properly handling join handles is a frequent source of errors. Forgetting to call .join can lead to orphan threads that might never finish, consuming resources.
Okay, let's say I want the spawn thread to do some heavy calculations and return a result. How would I use join handle to get that result?
You'd return the result from the spawn thread's closure, and then you'd get it when calling .join.
So, if you want to return something from a thread, you need to properly package the result within the thread closure. Is that right?
Exactly. Your calculation must return a value that you can access once you call .join.
Interesting. So, controlling the flow of execution within threads is critical in situations with complex operations.
Correct. Managing thread life cycles, using join handles, and paying close attention to where you place join is essential for writing robust concurrent programs.
Thanks, Russ Jackson. This has been super helpful. Great advice.
My pleasure, Matthew. Always happy to help.
Welcome back to the show, Russ Jackson. Today, we're diving deep into threads and closures in Rust. Let's start with the basics. What are closures, and why are they useful?
Closures are anonymous functions, little blocks of code you can define right inside another function. They're handy because they can remember and use data from the surrounding environment.
So, they're like mini programs within a program?
Exactly. They're super flexible, but that flexibility comes with some tricky ownership rules, especially when you throw them into threads.
What are threads, and how do they relate to closures?
Threads are like separate workers in your program. They let you do different tasks concurrently. Now, closures are great for passing data between threads, but you need to be careful.
Why? What's the catch?
Rust's ownership system. If a thread needs data from the main program, it needs to own that data, not just borrow it. Otherwise, the main program might change or delete the data while the thread is using it. That could crash the program.
So, how do we make sure the thread owns the data it needs?
We use the move keyword. It's like telling the closure, take ownership of this data, don't just borrow it.
Can you give an example of a use case where this is crucial?
Imagine an app that downloads files. Each file can be downloaded by a separate thread, and each thread needs the file's URL data. The move keyword ensures the thread gets a copy of the URL, preventing issues if the main program changes or removes the URL.
So, move essentially takes ownership of the data within the closure?
Right. If a closure uses move, it copies the data into its environment. This is different from borrowing, which just gives a reference.
What happens if you try to use drop on a variable after move?
You get a compiler error. Rust prevents you from messing up the ownership rules. That's important for reliability.
What if the data you're passing to the closure is something like a large vector, and a move operation is too costly?
You can still use move with large vectors, but there are options to avoid unnecessary copying by using references or borrowing smartly.
Let's talk about the example where drop is called after the thread is spawned. Why does the compiler complain if move is used?
Because the main program can't use the data anymore after it's been moved into the thread. This is a perfect example of Rust's strict ownership rules at play.
So, in short, we should use move for closures used in threads to ensure the thread has exclusive access to the data?
Correct. Move is essential for safe multithreading in Rust. It protects against data races and prevents dangling pointers.
What about financial applications? How could this be relevant?
Imagine a trading system where you need to process thousands of transactions simultaneously. Each thread could handle a set of transactions, but the data for each thread would have to be owned and moved.
Fascinating. Rust's ownership system is a strong concept. Russ Jackson, thank you for shedding light on this.
Thanks for having me.
Welcome back to the show, Russ Jackson. Today, we're diving deep into message passing in Rust. Can you give us a high-level overview?
Sure, Matthew. Message passing is a great way to manage concurrency safely. Instead of threads directly sharing memory, they communicate by sending messages. Think of it like a postal service for your program.
A postal service for your program? That's a helpful analogy. How does this work in practice with Rust channels?
Rust channels are like one-way streets, or better yet, a river. You have senders on one side and a receiver on the other. Senders put data into the channel, and receivers get it. It's a safe way to transfer data between threads.
So, multiple senders, one receiver. Is there a limit to how many senders can push data?
Exactly, Matthew. That's the multiple producer, single consumer, MPSC model. It's perfect for situations where you have many tasks generating data that needs to be consolidated by a central processor.
Cool. Let's look at some code. You have a channel created. What does that mean?
We create a channel using MPSC, channel. This function returns a pair, a transmitter, TX, and a receiver, RX. Imagine a pipe connecting two parts of a system.
Okay, so we got a pipe. What's next?
Next, we move the transmitter, TX, into a separate thread using thread, spawn. The thread sends a message, hi, through the channel. It's like sending a letter through the mail.
And the main thread receives that message?
Yes, the main thread waits for a message using rx.rect. It gets the message, then prints it out. Crucially, the receiving thread waits for the message, preventing potential errors that can happen if you access shared memory between threads without appropriate synchronization.
So it blocks until a message arrives. What if there are no messages?
If the sending end of the channel is closed, rect will return an error. That's important for robustness. In real-world applications, we'd need more sophisticated error handling.
If you had extra work to do in the main thread before receiving a message, how would you handle that?
We'd use try_rect. It checks for a message without blocking the thread. If there's no message, it returns error, allowing the thread to perform other tasks.
So, try_rect is non-blocking, while rect blocks. That's a key difference. What are the real-world applications of message passing?
Think of a trading platform. Many traders generate data, orders. A central system, a single receiver, processes these orders. Message passing ensures concurrent data transfer and prevents conflicts.
So, the sender-receiver model is safe, even with multiple producers. What are the potential pitfalls?
A major pitfall is forgetting to close the channel. This can lead to resource leaks. A closed channel signals that no more messages will be sent, allowing the receiver to gracefully end its task.
What about using channels to create something like a chat application?
Absolutely. Each user could be a producer sending messages. The main thread acts as the receiver to display messages.
A compelling example. Let's say you have a situation where a producer sends a lot of data. Is there a way to make sure the consumer keeps up?
You could introduce buffering to the channel, allowing the receiver to catch up and prevent the sender from being blocked.
Excellent points. Russ Jackson, thank you for illuminating message passing in Rust. It's a powerful tool, and understanding the potential pitfalls is crucial.
My pleasure, Matthew. It was a great discussion.
Russ Jackson, welcome back to the show. Let's dive into this concurrent thread example. This code snippet shows a channel sending multiple values. Can you break down how it works?
Sure, Matthew. We have a channel, TX, RX, which is the essential communication pipe between our threads.
So, the sending thread sends multiple messages?
Yes, a vector of strings, and it pauses between each one using thread, sleep.
That pause is key. Why is that important?
It shows the concurrent nature, proving both threads are running simultaneously, not sequentially.
How does the receiving thread wait for the messages?
It uses RX as an iterator. Each message coming through the channel causes a call to println in the receiving thread, printing out the received message.
Interesting. This is like a queue, with the sender adding to the queue and the receiver processing the queue items one by one?
Exactly. The RX acts like a queue, grabbing the messages as they become available. The channel closes after all values are sent.
Crucially, The receiver doesn't actively poll for data. The code just waits?
Exactly. The for loop over Rx implicitly waits for the messages to be available.
So, a fundamental aspect of this design pattern is the iterative receipt in the receiver's thread, right?
Yes. It's an elegant way to handle asynchronous data. The receiver does not have to actively check. The channel manages the flow.
This method prevents the receiver from having a busy wait loop, like continually checking if data is available. That saves CPU cycles, right?
Precisely. It optimizes resource utilization. In real-world apps, this is critical to avoiding performance bottlenecks.
What if the sender thread panics before sending all the messages?
The channel would likely remain open. The receiver would likely end upon channel closure, but not before printing all the elements received.
A subtle difference that could have unexpected consequences.
Absolutely. Careful handling of potential errors is paramount in concurrent programming.
So, what are some potential applications for this kind of concurrent data flow?
Real-time data processing, financial data feeds, or any operation where multiple parts of the program need to communicate asynchronously.
So, these are common in financial applications where fast transaction processing is key?
Exactly. If you're processing market data, for instance, the ability to receive updates in a timely manner, without blocking the main thread, is critical.
That's really helpful. Russ Jackson, thanks for breaking this down. We've seen how multiple threads can communicate efficiently using channels, and the vital role of the receiver being a passive iterator. This is invaluable for designing robust and high-performance systems.
Thanks for having me, Matthew.
Russ Jackson, welcome back to the show. Let's dive into creating multiple producers for a single consumer. How does cloning the transmitting half of a channel work?
Hey, Matthew. Great question. So, in a multi-producer, single consumer, or MPSC channel, you have one receiver, Rx, and many senders, TX. The key is sharing the resource safely. Cloning the sender allows us to create multiple sending handles from a single channel.
So, we create a copy, but it points to the same underlying channel, right?
Exactly. Cloning doesn't duplicate the channel itself. It creates a new sender that can interact with the same receiver queue. Imagine a bank teller window. You, the first sender, can give the teller, the receiver, a deposit slip. The clerk takes the deposit slip. Then a new employee, another sender, cloned from the first, can also hand the clerk another slip. They all go into the same queue.
Brilliant analogy. How does this avoid conflicts in sending?
The channel's internal mechanisms manage the order and prevent data corruption. Think of the queue as a numbered receipt system. Each deposit slip gets a number, and the teller processes them in sequence. This prevents simultaneous access, ensuring data integrity.
So, we essentially have a shared resource, but the senders work independently with the guarantee the receiver will handle one message at a time, correctly?
Precisely. This is where channels help in concurrent programming. It's a fundamental mechanism to coordinate tasks safely.
Okay, so this approach could be valuable in financial applications. Like if many traders need to post market orders onto an exchange feed?
Absolutely. Imagine a high-frequency trading platform. Multiple traders can send orders independently, while the exchange's order processing system, the receiver, handles them in a synchronized fashion, preventing chaos and ensuring orders are processed correctly and timely.
But what if a sender fails? Does it impact the other senders?
The failure of one sender does not usually directly impact the others, assuming there are no shared mutable resources outside of the channel. The channel itself handles this internal process. This is a key feature of concurrency, independence, and safety.
Fascinating. So, we can safely share resources by using channels and cloning sender. But what if you have a very large number of senders and the receiver can't process fast enough?
The receiving end might be overwhelmed if the sending is too rapid. It's similar to a clogged highway, you know? It's important to consider the balance between the rate of sending and processing at the receiver. It's possible to have buffer overflow issues.
So, we might need to implement some kind of throttling or queue management logic on the sender side to prevent overwhelming the receiver. Is that right?
Absolutely. You might implement mechanisms to ensure sending rates are controlled to prevent buffer overflow.
Thanks, Russ Jackson. Great insight. That was a very informative explanation of how channels work. Now it's all clear. Russ Jackson, welcome back to the show. Today we're diving into mutexes. Can you give us a quick overview of what they are?
Sure, Matthew. Mutexes, short for mutual exclusion, are like digital gatekeepers. They only allow one thread to access certain shared data at a time. Think of a single microphone at a panel discussion.
That's a great analogy. So, how does a thread actually gain access?
A thread has to request the mutex's lock. It's like asking for the microphone. Once granted, the thread has exclusive access to the protected data.
And what happens when it's done?
It unlocks the mutex, freeing it up for another thread to use, passing the mic to the next speaker, so to speak.
Crucially, it seems that forgetting to unlock is a common problem.
Absolutely. If a thread grabs the lock but never releases it, other threads are blocked. This is a major pitfall in multi-threaded programming.
So, what are the benefits of using mutexes?
They prevent data corruption, ensuring data integrity when multiple threads access it.
What if multiple threads need that data?
They'd be waiting in line, one at a time, accessing the shared resource.
Are there drawbacks? This kind of sequential access seems slow.
Well, yes. It reduces concurrency. It's about trade-offs, protecting data integrity versus speed, you know?
Rust-type system and ownership rules play a role here, right?
Exactly. Rust's design prevents common locking errors. You can't forget to unlock.
So, are mutexes always the answer?
Not necessarily. If you're not dealing with multiple threads trying to access the same data, a mutex is overkill. Channels can be a more lightweight approach in such cases.
Can you give me a real-world financial example?
Imagine a bank's transaction processing system. A mutex ensures only one transaction is processed at a time to maintain account balance accuracy. If you didn't use a mutex, you might end up with an incorrect balance.
So, it's essential for preventing inconsistencies.
Correct. It safeguards critical financial operations from data corruption.
How do you debug a locking problem in a multi-threaded scenario?
Debugging is hard sometimes. The problem isn't always where you expect it to be. Logging is often key.
Rust's strong type system, again, makes debugging easier?
Exactly. You can usually spot the error quicker. It's like having an extra set of eyes.
Thanks for clarifying this. Mutexes are important tools, but they need to be used correctly.
Absolutely. Understanding the trade-offs and knowing when a mutex is appropriate are key.
A powerful concept, Russ Jackson.
It is, Matthew. Always about balance in programming.
Russ Jackson, welcome back to the show. Today we're diving deep into mutexes. Can you give us a high-level overview?
Sure, Matthew. Mutexes are a critical part of concurrent programming in Rust. They let you safely share data between threads. Imagine a shared bank account. You need a way to prevent multiple people from trying to access and change the balance at the same time, causing problems.
Right? That's a great analogy. So, how does a mutex work?
A mutex, short for mutual exclusion, acts like a lock. Only one thread can hold the lock at a time. When a thread wants to access shared data, it acquires the lock. Other threads are blocked until the lock is released.
Okay, I see. So, how is that implemented in Rust code?
We create a mutex using a function and wrap the data we want to protect within. Then, we use the lock method to grab the lock. It's blocking until the lock is available.
So, if a thread is trying to lock a mutex that's already locked, what happens?
It gets blocked. This is crucial for avoiding data races, where multiple threads corrupt shared data.
What about error handling? Is there any way to prevent the program from crashing in case of issues?
Yes, the lock method returns a result. We can use unwrap to handle the success case. However, unwrap can cause a panic if the lock isn't available, so it's not ideal for production code. We should use lock.expect failed to acquire lock, which provides a helpful error message for debugging. This makes the code more robust and gives us more information if something goes wrong.
Got it. And the mutex guard?
The lock method returns a mutex guard, a smart pointer. Crucially, it automatically releases the lock when it goes out of scope. This prevents deadlocks and ensures the resource is always freed when it is no longer needed.
That's a critical point. Why is this automatic release so important?
Imagine if you forgot to release the lock. Other threads would be perpetually blocked, and your program would hang.
So, what about the type system? How does it ensure proper locking in this example?
The type system enforces the rule that you must acquire the lock before using the data within the mutex. It ensures you're working with the data in a way that avoids data races and corruption. This prevents subtle errors that can happen in concurrent programs in languages like C/C++ that are less strict.
What are some common pitfalls to watch out for when working with mutexes?
One pitfall is forgetting to release the lock. Another is using unwrap, when you might need more robust error handling.
Is there a use case where something other than unwrap might be appropriate?
In certain cases, like a function that's handling a very short operation with a mutex, using unwrap might be okay, but for anything more complex, a more general approach is recommended.
What about performance implications? Can mutexes impact performance in certain circumstances?
Mutexes can introduce a performance overhead compared to single-threaded operations, especially under heavy contention. This happens when multiple threads compete for the same lock very frequently.
So, Russ Jackson, are there alternatives to mutexes in some specific cases?
Yes, there are other synchronization primitives in Rust, such as atomic variables or channels, which can be more efficient for specific scenarios, but mutexes give a simple solution for most data protection.
Excellent points. Russ Jackson, thanks for the insights. This was truly enlightening. Russ Jackson, welcome back to the show. We're diving deeper into thread safety today, specifically using mutex. The previous example had a compiler error. Can you explain what went wrong and how we fix it?
Sure, Matthew. The problem was trying to move the ownership of the mutex into multiple threads. Rust's ownership system prevents this because it's crucial for avoiding data races. Imagine multiple threads simultaneously trying to change a bank account balance. Chaos!
So, the error message was telling us this. But why didn't the loop version cause the problem?
The loop version, while it had multiple threads, each thread got a unique copy of the mutex. The problem only arises when there's a single mutex object shared between multiple threads that are modifying it concurrently.
Okay, so we can't just move the mutex. What's the solution? How do we allow multiple threads to access the mutex without the race condition?
Exactly. The solution involves using the ARC type, which stands for Atomic Reference Counting. ARC lets us create multiple owners of the data, so we don't have to move the ownership into the thread.
So, we need to change how we create the mutex, not just how we use it.
Exactly, we can't just move the mutex. Instead, the ARC wrapper allows multiple references to the data to be created while maintaining safety.
Okay, let's say I want to use a counter. How do I use it now?
We'll create an ARC. This combines the atomic reference counting with the mutex for safe concurrent access.
Okay, and what if one thread needs to lock the mutex for a very long time? How does that affect other threads?
If one thread holds the lock for a substantial period, it blocks other threads from accessing the shared data, potentially leading to performance issues. Careful lock management is crucial to avoid deadlocks or starvation.
So, the mutex acts like a gate, preventing accidental modifications by multiple threads?
Yes, and with ARC, we are not giving up control of the resource to the threads. Rather, we make many copies that all reference the shared resource.
What's an example of when this type of structure might be helpful in finance?
In high-frequency trading, where multiple threads need to access and update market data or trading positions, the safety and efficiency of ARC are crucial for preventing race conditions and data inconsistencies.
That makes sense. Any potential pitfall we should be aware of?
Carefully consider the trade-off between the overhead of atomic reference counting and the potential performance impact on multi-threaded applications.
That was great, Russ Jackson. Any final thoughts on using mutexes in Rust?
Always remember, using shared mutable data in concurrent environments needs careful consideration. Employ the correct tools, like ARC, and strategies to achieve both safety and performance.
Thanks again for the insights, Russ Jackson. Russ Jackson, welcome back. Let's dive into this multiple ownership with multiple threads issue. We were trying to use RC with mutex. What went wrong?
Yeah, Matthew. We were trying to share a mutex, a lock, between multiple threads using RC, which is a reference-counted smart pointer. But RC isn't thread safe.
So, RC isn't thread safe? Why not?
Well, RC manages its reference count. It increments when you clone and decrements when a clone goes out of scope. But it doesn't use any mechanisms to stop those changes from getting messed up when multiple threads are involved. Think of it like a shared bank account. If several people try to deposit and withdraw money simultaneously, without proper controls you might end up with erroneous balances. That's precisely what can happen with RC in a multi-threaded environment. It's a race condition waiting to happen.
So, what kind of problems could this cause in a financial application, for example?
Imagine a stock trading platform using RC4 shared data. If multiple threads tried to simultaneously update the price of a stock, incorrect values could propagate, leading to potential trading losses and significant financial repercussions. A race condition is definitely an enemy in any serious system like finance.
Okay, that makes sense. So, the compiler is telling us it's unsafe to use RC with mutex and multiple threads. What's the solution?
We need a type that's explicitly designed for concurrent access. ARC is the solution. It's like RC, but it is built on top of the concurrency primitives provided by the standard library, making it thread-safe.
ARC? Like a special, armed RC? Can you tell me more about ARC?
Exactly. ARC stands for Atomic Reference Counted Smart Pointer. It performs all the reference counting operations in a way that's safe for multiple threads to use. The atomic part ensures that the reference count is managed using atomic operations that prevent conflicts from occurring between concurrent threads. This ensures that no two threads modify the count at the same time, protecting against corruption.
So, if we replace RC with ARC, things will be thread safe, preventing those race conditions?
Absolutely. Using ARC ensures the safety and integrity of reference counting, preventing the type of errors we encountered before in multi-threaded scenarios. It's crucial when dealing with shared resources in concurrent programs.
That's helpful to understand. A crucial difference is thread safety. So, is there a simple rule to remember when dealing with concurrency and smart pointers?
Yes. When sharing data across threads, you absolutely need a thread-safe data structure. ARC is that tool in the Rust toolbox. RC is great, but in scenarios requiring concurrency, ARC is your go-to. This extends beyond simple data sharing to control access and updates to data, securing against potential errors arising from concurrent access.
So, always choose ARC over RC when dealing with threads?
Well, RC is good for single-threaded environments. But for multiple threads, ARC is essential to avoid race conditions and ensure data integrity. It's the crucial difference.
Thanks, Russ Jackson. That clears up a lot. We'll definitely be keeping ARC in mind from now on. Russ Jackson, welcome back. We're diving deeper into Rust's concurrency tools today. You mentioned RefCell and mutex. Can you elaborate on their similarities?
Sure, Matthew. Both RefCell and mutex allow for mutable access to shared data. They're both ways to get around Rust's strict immutability rules.
So, both are about mutable interiority?
Exactly. RefCell gives you mutable access safely within the confines of a single thread. Mutex, however, extends this concept to multiple threads, offering a way to share data across threads safely.
Okay, but what are the crucial differences? Why would you choose one over the other?
RefCell is faster because it doesn't use locks. Mutex, on the other hand, is crucial for concurrent programs where several threads need simultaneous access to shared data.
So, if I have a scenario with only one thread, RefCell is the way to go?
Precisely. RefCell is significantly more efficient for single-threaded contexts, but it lacks the safety features of mutex when dealing with multiple threads.
Okay, so mutex is thread safe. And you mentioned a risk with mutex?
Yes, deadlocks. Imagine two threads trying to access shared resources. If thread A holds one lock and needs the other, and thread B holds the other lock and needs the first, they're stuck, a deadlock. It's a critical thing to consider.
Wow, that sounds tricky. Are there ways to avoid deadlocks?
Absolutely. Careful resource management is key, along with understanding the dependencies between resources. Good design patterns and careful planning are crucial. For example, acquiring locks in a consistent order can minimize the risk.
Sounds like a whole new set of complexities.
It is. You need to meticulously plan concurrent access patterns to prevent these kinds of issues. The standard library documentation has great guidance on handling such cases.
So, let's talk about those reference cycles you mentioned with RC. Something similar exists with mutex?
Yes, very similar. Just as with RC, you can inadvertently create reference cycles with ARC, a common pitfall when sharing resources.
This is starting to sound like a carefully balanced act. So what do these tools actually mean practically for a software engineer?
In financial applications, mutex is indispensable for managing shared data and transactions across multiple concurrent users or processes, while RefCell can efficiently serve a single user or thread without the overhead of locking.
So, it's about making trade-offs to make efficient use of resources?
Exactly. Understanding the strengths and weaknesses of each tool is vital for building robust and efficient Rust applications, especially in financial contexts.
Russ Jackson, thanks for illuminating this aspect of Rust for us.
My pleasure, Matthew.
Russ Jackson, welcome back to the show. So, we were talking about thread safety in Rust. Can you elaborate on this send marker?
Sure, Matthew. The send marker trait is crucial for ensuring safe data transfer between threads.
So, it's like a passport for data?
Exactly. It says, this data is safe to send to another thread without causing problems.
What kinds of problems are we talking about?
Things like race conditions, where multiple threads try to access and modify the same data at the same time, leading to unpredictable results. The send marker helps prevent that.
Okay, so almost every type in Rust has the send marker?
Almost. Crucially, the RC type doesn't.
Why not?
Because RC, reference counting, uses reference counting. If you clone an RC and send the clone to another thread, both threads could try to decrement the reference count simultaneously, which is a disaster.
So, RC is for single-threaded situations?
Precisely. It's optimized for single threads where performance isn't crucial.
So, using ARC instead is the solution when you need thread safety?
Exactly. ARC, atomic reference counting, is similar to RC, but it's designed for multiple threads. It uses atomic operations to ensure safe reference counting across threads.
So, if you accidentally try to send something like RC, what happens?
You get a compilation error, because the type RC is not send.
Okay, so what's the rule of thumb for when to use send types?
Use send types when you need to transfer ownership of a value between threads. You want to avoid race conditions and data corruption by making sure the data is thread safe.
This send marker is pretty critical then for avoiding issues like data corruption?
Definitely. It's an important part of ensuring the correctness and reliability of your Rust programs, especially in concurrent applications.
And if a type is composed entirely of send types, it inherits the send property?
Absolutely. It's a nice property of the Rust type system. This simplifies writing concurrent code, preventing accidental errors.
What about primitive types? Are they generally send?
Yes, almost all primitive types are send, except for a few special cases like raw pointers, which we'll cover later.
So, the choice between RC and ARC depends on thread safety needs?
Correct. RC is faster for single-threaded use cases, but ARC ensures thread safety and is the way to go for concurrent code.
This all seems like a pretty crucial aspect of preventing major errors in concurrent code.
Absolutely. The send trait is a fundamental tool for writing robust and reliable multi-threaded applications in Rust.
Thanks, Russ Jackson. This has been extremely helpful. Russ Jackson, thanks for joining us today. We're diving deep into the world of Rust concurrency, and today's topic is crucial: the send and sync traits. Can you explain why we don't usually need to implement them manually?
Yeah, absolutely. These traits, send and sync, are marker traits. They don't have any methods. They just tag types to tell the compiler if they can be safely sent between threads or used in shared memory.
So, they're like labels?
Exactly. If a type is built from other types that are already send and sync, the compiler automatically infers that the new type also has those properties.
So, it's a shortcut, essentially?
Precisely. The compiler handles the heavy lifting, avoiding manual implementation. This makes concurrent programming in Rust safer.
Okay, but what happens if we do need to implement them manually?
Then we're venturing into unsafe Rust code. That means we're taking on the responsibility of ensuring the type is safe for concurrent use.
Unsafe code? Sounds risky. Why would we even want to do that?
Well, you might encounter a situation where you're creating a custom data structure that's not built from other send and sync types. Imagine a financial application, let's say a trading platform.
A complex trading platform? That's a great example.
You might be working with data structures that aren't inherently thread-safe. You need to ensure these structures meet the requirements, so the trading algorithm works correctly. Manually implementing these traits gives you fine-grained control.
That makes sense. So, where's the danger? What could go wrong?
If you don't implement them correctly, you introduce concurrency bugs that could lead to unpredictable behavior in your application, potentially causing data corruption or crashes, which could be catastrophic in a financial context. Think about an order processing system. If multiple threads try to modify the order data simultaneously without proper safeguards, things could get very messy very quickly.
So, when is implementing them manually the best option for a trading application, given the risk?
It's really about knowing precisely how your custom data structure interacts with multiple threads. It's a very specialized situation, a specialized task. If you're not confident in your implementation, it's much safer to use compiler-guaranteed safe types.
So, it's a trade-off between safety and control?
Absolutely. The compiler-based solution is safer, but the manual implementation gives developers direct control over concurrent data management when required.
Thanks for the excellent explanation, Russ Jackson. This sheds a lot of light on the practical implications of these traits, especially for complex financial applications.
Anytime. The Rustonomicon is a great resource for further learning on upholding these safety guarantees. It explores the specifics.
Great insights, thanks again. Russ Jackson, welcome back. We're diving deeper into concurrency in Rust today. So, you mentioned crates. Can you elaborate on why they're crucial for concurrency in Rust?
Absolutely. Rust's concurrency model is designed to be safe, but the specifics are often handled by libraries. These crates are like third-party extensions, right? They offer more robust and up-to-date solutions than the standard library sometimes.
So, they're like specialized tools for different concurrency needs?
Exactly. Imagine you need a highly performant queue for your trading platform. You might find a dedicated crate designed for that, instead of building one from scratch. That's why keeping tabs on these crates is important.
What about the standard library tools for concurrency? Are they inadequate in any way?
No, they're essential. Think channels, a way to send messages between threads without shared memory, and mutex, used for locking, or arc for safe reference counting across threads. They're safe because the Rust compiler catches problems. It checks for things like data races and dangling pointers, so you can have the safety that you need.
So, you're saying the compiler basically ensures safety?
Yeah, that's right. The compiler, helps a lot. The borrow checker ensures there are no data races, making it easier to build correct concurrent programs.
This safety sounds great, but how does it affect performance? Does it slow things down significantly?
Not really. While the safety features add some overhead, it's usually minimal in comparison to the benefits. You don't have to worry about debugging those tricky threading errors, which can be a major time saver and cost reduction in real-world projects. It's a trade-off. The added assurance of no races is generally worth it.
Right, it reduces debugging time. So, we're transitioning to more sophisticated program structures now. You talked about modeling problems better. How do Rust idioms compare to object-oriented approaches?
Rust's idioms are different. It focuses on ownership, borrowing, and lifetimes, unlike the object-oriented encapsulation. But you can find parallels. Both can structure code to improve readability and maintainability, even though their approaches are different.
You are saying that, while the styles are different, the goals are the same?
Precisely. The goal is to write code that's easy to reason about, easy to test, and less prone to errors. So, it's more about how you approach problem-solving than the object-oriented style, which also has its merits.
Fascinating. So, Rust concurrency features are designed to prevent common concurrency errors in other languages.
Absolutely. Rust's strong type system and the borrow checker are key. It's a fundamentally different design philosophy, but one that prioritizes safety and reliability in a way that can improve overall project quality and cost-effectiveness.
Thanks, Russ Jackson. This has been insightful.